Welcome to this model. You are watching Vlsi Design Lecture Series. Today we are going to see about the combinational MOS logic circuits. Let us see about static CMOS. The most widely used logic style is static complementary CMOS. The static CMOS style is really an extension of the static CMOS inverter to multiple inputs. To review the primary advantages of CMOS structure is robustness, its good performance and low power consumption with no static power dissipation. Most of these properties are carried over large fan-in logic gates implemented using a simple circuit topology. The complementary CMOS circuit style falls under a broad class of logic circuits called static circuits, in which at every point in time each gate output is connected to either VDD or VSS via a low resistance path. Also, the output of the gates assumes at all times the value of the Boolean function implemented by the circuit. This is in contrast with the dynamic circuit class, which relies on the temporary storage of signal values and capacitance of high impedance circuit nodes. So the later approach has the advantage of resulting gate is simpler and faster. Its design and operation are, however, more involved and prone to failure because of the increased sensitivity to noise. So that's why static CMOS is preferred in all cases. So combinational circuits are those whose outputs depends on only present inputs, and while sequential circuits have memory. Static CMOS circuits with complementary NMOS pull-down and PMOS pull-up network are used for vast majority of logic gates in integrated circuits. So here are some of the advantages of static CMOS. One is good noise margin, fast, low power, insensitive to device variations, easy to design, widely supported by CAD tools, readily available in standard cell libraries. Static CMOS in a logic circuit design technique whereby the output is always strongly driven by it is always connected being connected to either VCC or ground. This design is in contrast to dynamic CMOS, which relies on the temporary storage of the signal values in the load capacitances. A static CMOS circuit is composed of two networks, pull-up and pull-down network. A pull-up network is nothing but a set of PMOS transistors connected between VCC and the output line. The pull-down network is a set of NMOS transistors connected between ground and the output line. So this diagram shows an implementation for a random logic function called D plus A into B plus C. So for this B plus C function, you have the two transistors in parallel connection. The multiplication should have series connection, so A is in series with B plus C. And for these combinations, D should be in parallel. So here the D transistor is connected in parallel. So this must be inverted and the pull-up network, that is B and C are in series with and is in parallel with A, which are in series with D. A transistor can be thought of as a switch controlled by its gate signal. An NMOS switch is on when the controlling signal is high and is off when the controlling signal is low. A PMOS transistor acts as an inverse switch that is on when the controlling signal is low and off when the controlling signal is high. The pull-down network is constructed using NMOS device, while the PMOS transistors are used in pull-up network. The primary reason for this choice is that NMOS transistors produce strong zeros and PMOS devices generate strong ones. Now let us consider an example. The output capacitance is initially charged to VDD. Two possible discharge scenarios are seen. One is an NMOS device pulls the output all the way down to ground, while the PMOS lowers the output no further than VTP. The PMOS turns off at that point and stops contributing discharge current. NMOS transistors are thus the preferred devices in the pull-down network. Similarly, two alternative approaches to charging up a capacitor are shown, with the output initially at ground. A PMOS switch succeeds in charging the output all the way to VDD, while the NMOS device fails to raise the output at above VDD minus VTN. This explains why PMOS transistors are preferentially used in pull-up network. So a set of rules can be derived to construct logic functions, that is NMOS devices connected in series correspond to AND function. With all inputs high, the series combination conducts and the value at one end of the chain is transferred to other end. Similarly, NMOS transistors connected in parallel represent an OR function. Conducting path exists between the output and the input terminals if at least one of the input is high. So, using similar arguments, construction rules for PMOS networks can also be formulated. A series connection between the PMOS transistors conducts if both inputs are low, representing NOR function, while PMOS transistor in parallel implement a NAND function. So, using De Morgan's theorem, it can be shown that the pull-up network and pull-down networks of a complementary CMOS structure are dual networks. This means that a parallel connection of transistors in the pull-up network corresponding to a series connection of corresponding devices in the pull-down network and vice versa. Therefore, to construct a CMOS gate, one of the networks, that is, like for example, if I take pull-down network, is implemented using combination of series and parallel devices. The other network is obtained, for example, pull-up network, using the duality principle by walking the hierarchy, replacing series subnets with parallel subnets and parallel subnets with series subnets. The complete CMOS gate is constructed by combining the pulled-up network with pull-down network. And the complementary gate is naturally inverting, implementing only functions such as NAND, NOR, and XNOR. The realization of non-inverting Boolean function, for example, AND or XOR, in a single stage is not possible and requires an addition of extra inverter stage. The number of transistors required to implement n input logic gate is 2n, which means that, for example, if you take this example, you have four variables, four inputs. So the number of transistors required would be 2n, which is equal to 2 into 4 is equal to 8 transistors. So which means that here we are using 4 NMOS transistors and 4 PMOS transistors, totally 8 transistors are required. CMOS stages are inherently inverting, and so AND and OR function must be built from the NAND and NOR gates. So De Morgan's law helps with this conversion. A dot B the whole bar is equal to A bar plus B bar, and A plus B the whole bar is equal to A bar dot B bar. An AND gate is equivalent to an OR of inverted inputs. An OR gate is equivalent to AND of inverted inputs. Switching between these representations is often called bubble pushing. Static CMOS also efficiently handles the compound gates computing various inverting combinations of AND and OR functions in a single stage. The function f is equal to AB plus CD can be computed with an AND or invert gate and an inverter. In general, the logical effort of the compound gates can be different for different inputs. And this diagram shows how logical efforts can be estimated for AOI21, AOI22, and a more complex compound AOI gate. The transistor widths are chosen to give the same drive as unit driver. The logical effort for each input is the ratio of the input capacitance of that input to the input capacitance of the inverter. For the AOI21 gate, this means that the logical effort is slightly lower than the OR terminal than for the two AND terminals. The parasitic delay is estimated from the total diffusion capacitance on the output node by summing the sizes of the transistors attached to the output. So this diagram shows the logical effort and parasitic delay of AOI gates, that is AND or inverted gates. Some logic gates like AOI21 are inherently asymmetric in that one input has less capacitance than other. Other gates like NAND and NOS are nominally symmetric but actually have slightly different logical effort and parasitic delays for the different inputs. When one input is far less critical than another, even nominally symmetric gates can be made asymmetric to favor the late input at the expense of early one. In a series network, this involves connecting the early input to outer transistors and making the transistor wider so that it offers less series resistance when the critical input arrives. In a parallel network, the early input is connected to a narrower transistors to reduce the parasitic capacitance. Inverters with the different beta ratios, that is R is equal to beta P by beta N, are called skewed inverters. Beta is proportional to W by L. If R is greater than 1, the inverter is said to be high skewed, which means the W by L of PMOS transistor should be greater than W by L of N. If R is less than 1, the inverter is low skewed. That is, if W by L of P is less than W by L of N. If R is equal to 1, the inverter has normal skew or unskewed, which means that WL by L of P is equal to W by L of N. Skewed gates reduce the size of the non-critical transistors. High skew gates will favor the rising output transition for small NMOS, and the low skew gates will favor the falling output transitions for small PMOS. And this diagram shows the logical efforts for unskewed and high skewed and low skewed values. So, and for this example, in this example, for a unit inverter, the high skewed inverter has an NMOS transistor divided by the value of the unit inverter, that is 1 by 2 is applied to NMOS here. Similarly, for low skewed, PMOS has 1 by 2 value of the unit inverter, that is 2 by 2 gives a value of 1 here. Thank you.